First speaker this morning is Jeremy Quastel from University of Toronto, and he will talk about the KPZ fixed point, the first of two talks.
Thanks. The organizers.
Microphone.
Yeah. So the organizers, the real organizers, asked me to give a couple of talks on the fixed. How do you do this?
If you don't do it.
Oh, there it is. Okay. Asked me to give a couple of talks on the fixed point.
Can you recording?
Yeah. All right. So what I'll try to do is today I'll tell you about the fixed point itself, and tomorrow I'll talk to you about TASEP and how you actually get the thing. So it's supposed to be an expository talk, so please ask questions. So we are, in general, in KPZ, we have this fluctuating interface moving this way in principle of a stable phase invading an unstable phase. And we're always over a one-dimensional substrate in this talk. So this is called 1 + 1 dimensions. And the interface we're going to assume for simplicity is just a height function. So x is this space and t is time. And the thing's fluctuating and moving up. Okay? And there's lots of models. The most famous model is this KPZ equation. That's DTH. Oh, most of you know this. This is space-time white noise forcing. This is a term which relaxes the surface. And then the key term is this nonlinear term, which is because these interfaces don't really know that they're growing up. They're just growing, and they're going in all directions at the same time. So really the growth is supposed to be like that. And of course, if you have, I didn't draw it very well, I should have drawn it here. If you're going out, then the vertical growth is a nonlinear function of the slope. And so that's the simplest nonlinear function, so you put it in there. Okay, so that's the KPZ equation. Now, mostly what people talk about is well-posedness of this equation. I'm completely unconcerned with that in this talk. We're interested in large-scale behavior. Okay. So what's been observed in these systems is that the growth is at some rate, some constant rate of time. So you've got some CT, where this C is some non-universal constant. It depends on the models. But then the universal thing that one sees is that the size of the fluctuation here is size t to the 1/3. And it lives on a spatial scale of t to the 2/3. And you see some universal fluctuations there in the limit of very large t. Okay, and so that's what I want to talk about. But another way to say this is that if I look at these interfaces and I rescale like this, well, if you do that, you've looked at a very, very long, epsilon's a small parameter. You've looked at a very, very long time scale, so you expect the thing to go flying up, so you need to subtract some huge constant to shift the thing back and see these fluctuation processes. And so what you believe is that this rescaled object, h epsilon tx, should converge to some universal limit. I'll call it h bar tx. And this is the type of thing we want to study. Okay? So we're interested in what this universal limit looks like. In particular, we'd like to compute the distribution function of it. That would be nice. Or maybe more aggressively, the multidimensional distributions. So these are the type of things one would like to compute. Okay? Now, these things came from Markov processes, so one believes that the H is a Markov process. And as I'll show you in a second, it remembers the initial data. So they're really Markov processes. So HTX is a Markov process, and this type of data tells you what's the transition probabilities. That's enough to tell you what's the transition probabilities. So we basically have a Markov process of evolving functions, and we'd like to know its transition probabilities. Okay. All right, just a few things about scaling. There's a few invariances of this process. So first of all, the process definitely has the following scaling invariance. So it's invariant under that scaling. It's scaling invariant because it was achieved that way. In a second, we'll also see that it has the invariance skew time reversal. Okay, so these are the two important invariances. The skew time reversal is very important for us. Okay. Okay. Now, I think this is a bit unusual in this crowd. Everything's derived by algebra, not by analysis. And we definitely can't treat the KPZ equation. So it's all about a special discretization of KPZ called TASEP. Okay. Now, TASEP, the height functions are assumed to be simple random walk paths. Simple random walk path just means that it goes up or down at each step. So it's a function over the integers. So now x and z. And it looks like this. So Ivan drew one last time. Okay, so that's the state space. Looks like that. They're just functions which, from x to x plus 1, they just go up or down by 1. Okay? And then the rule in TASEP is just that peaks jump to valleys at rate 1. And all the peaks are trying to do this independently at rate 1. And that's the whole rule. So that's TASEP. Okay. Nice thing about TASEP is that simple random walk paths is invariant. So if you start the thing as a random walk, you just flip a coin at each site to decide whether it was an up or a down. And then you wait a while, you'll actually see the same distribution. Okay? Of course, it's terribly coupled with the initial one. It's not the same thing, but it's, if you just forget about all that, what you see is another simple random walk path. Over here, for KPZ, grounded motion is invariant. In fact, Brownian motion plus any row x is invariant. So any drifted Brownian motion is invariant for KPZ. Okay. And here, this simple random walk paths, you don't have to flip a fair coin. They're all invariant. Okay. Now, if you write an equation for TASEP, for the height function, it's very easy to write an equation. The equation is obviously dh is minus 2 indicator function that you had a peak, dt, plus some martingales. That's the equation for TASEP. It's not too hard to see that. And it perhaps doesn't look too much like a discretization of KPZ. Except when things only take values plus or minus 1, there's a lot of room. You can just check.
What is M?
Martingale. This is just, dm just means d sum martingale, and that should be, you should think of that as like the white noise over there. Right? All right, d mart. That's more clear. So, here's a fun little calculation. You can just check that this is exactly equal to a half. So grad plus is just the forward discrete difference operator. So grad plus of f is f of x plus 1 minus f of x. Grad minus is just the backwards one, f of x minus f of x minus 1. Laplacian is just the discrete Laplacian. Minus or plus? Minus 1. That's just exact calculation. So you see it's just a discretization of KPZ. And there's something rather funny, which is that in KPZ, I think all of you would believe the thing's going up. But look, it's going down. That's because if you're going to do height shifts, it's not too clear which way up or down is. Okay, so you have to be careful. All right. And now you can see the skew time reversal invariance is just completely obvious, right? This H, which is the KPZ fixed point, will inherit all symmetries of any model which converge to it. So this just look at TASEP. It's just completely obvious that minus TASEP backwards in time is the same thing as it forwards in time. It's not so obvious for KPZ, but it's true. Okay. So for this model has some fantastic solvability. It and 5 of its friends, plus 5 or 6 other special cases. They're called things like push TASEP and parallel update TASEP and things like that. So there's a bunch of variants of this model for which everything I'm going to talk about works. they have some fantastic solvability which allows you to do some things, and in the early 2000s there were a number of results. So let me just describe those to you. Okay. So they talk about very special initial data. So one very, very special initial data is a corner. So it's supposed to go off in all directions like that, right? So you start with a corner, and then you discover the following thing. So now you start with a corner, and now you do that scaling. Okay? And you discover that f(1) r plus x squared. Well, you see, you have to add an x squared at time one. The thing actually, after a while, looks like a parabola with little wiggles. It'll look like that, right? You go down and look like some parabola, and there's little wiggles on top of it. And so you should add this x squared. And you discovered that this is nothing but the GUE Tracy-Whittem distribution. And there's another special data. I'll say what they are in a second if you don't know. Another special data is this one. It's flat. And you discover that f(1) x r is the GOE Tracy-Whittem distribution with some funny factor. Okay. So what are these distributions? So first of all, although I wrote f(1), because of this scaling invariance, you could get f at other times, of course, for these special initial data. So I just wrote it like that. And then they would just scale, and we'll see that in a second. So what are these distributions? Well, they're first of all what you get when you start with either a Gaussian unitary or a Gaussian orthogonal matrix. So GUE just means a Hermitian matrix. So Aij bar. And you put in Gaussians independent as much as they could possibly do to satisfy that. Okay? So put in independent Gaussians into the matrix. And then, but let's say those Gaussians are variance around n. So n by n matrix. Okay, so you have an n by n matrix and the variance is n. Then you look at the maximum eigenvalue.
It's 1 over n.
Sorry? Yeah, I get this wrong every single time. So but when I get to the end, tell me what the mistake is. Yeah. Then if I look at the maximum eigenvalue, it looks like about Cn plus n to the 1/3 times some special distribution, and that has this GUE Tracy-Whittem distribution. Okay, so did I get the n right or wrong?
No, it's right.
And C is 2 or something. Yeah.
The I and J on Aij should be.
That you're definitely right. Yes. Thanks. Okay. Okay, and GOE is just the same except they're real. So it's real. And you have the same thing, except that now it's the GOE distribution. Okay, so that's where they came from originally in the early 90s. These things were computed, and they're given several different ways, and let me mention those. So FGUE of R can be either written as a Fredholm determinant, I minus k. So there's some operator k, which is associated to this thing, which I'll write in a second. And you look at this on L2 of r to infinity, and that r is what tells you what the r is in there. And the k is just, well, it's just some special thing called the area kernel. So k is k area uv. So in this talk, operators and their kernels will just be interchangeably used. Okay? So it's either an operator or it's the operator defined by the integral kernel, this. Okay? And so the area kernel is this, minus infinity to 0 of d lambda of area u minus lambda, area v minus lambda. And, well, maybe you don't know what's the area. Area double prime u. It's just a special function, the area function. If you like, it looks like this. I could give you some useless formula for it, but anyway, it's the area function. You can look it up. Just Google area function. You'll learn everything about the area function. Okay, so that's the formula, and okay, so you got a Fredholm determinant formula for the thing. Okay, what else? Well, there's another way to write it. You could also write FGUE of R is equal to e to the minus r to infinity s minus r q squared s ds, where q satisfies this Panlevet-2 equation plus 2q. That's called Panlevet-2. Okay, so there's two ways to write the thing, and then GOE. So let's write GOE. So, let's go up a little bit. Is also given by a determinant of a different kernel in the same way, and so you just have to say what's the kernel for the GOE instead of the GUE. And the kernel there is, well, strangely, if I didn't make a mistake. Oh, okay, I'm doing it from memory. I don't know where it went. Okay. Yeah, sorry. I hope the 2 to the thirds are right. Anyway, it's given by a formula like that, modulo a plus or minus in the 2 to the 1/3. Or FGOE is equal to e to the minus a half integral r to infinity of qs ds times the square root of FGUE of r, where q is the same q. So these are the kind of formulas one got. Okay. Oh, there's a little bit more. I got a little bit out of room here, so I'll write it here. So also in those two cases, there were formulas for the multidimensional distributions. So for f t x1 xn. And these were also given by Fredholm determinants. In these two cases only. But now K is an n by n matrix called extended kernel. So it's n by n. And it's on the product of L2 of Ri to infinity. Okay. So at any rate, the story was there were a couple of special initial distributions for which one could do a calculation. One arrives at Fredholm determinants, and there was a recipe which told you your initial distribution gave you some Fredholm determinant. Okay, so now we're going to go to the fixed point. How much time do I have? Okay. So first of all, what is the KPZ fixed point? So now we want to do. So now we want to do general initial data. Okay? Now first of all, H is going to be a Markov process. I have to tell you what the state space is. So you think it's just nice functions. But actually, that's not quite right. Because if you look at what's happening to the initial data under that scaling, this guy, well, it's being rescaled diffusively. So it narrows out. That's what's called the narrow wedge. Goes to that. So our state space has to include functions like that as normal functions. The state space, and it has to include that convergence in this topology, right? And you have to keep in mind it's that outward growth, right? So this is a natural thing because it just grows outwards like this, you know. It's totally natural, okay? So the state space is actually, you see as upper semi-continuous functions. And upper semi-continuous functions, a function is upper semi-continuous if and only if it's hypograph. What is a hypograph? You have a function, the stuff below it's called the hypograph. Below and equal to the function. Function's upper semi-continuous if and only if its hypograph is closed. Closed sets have a nice topology on them, the Hausdorff topology. So upper semi-continuous functions are equipped with a nice topology, the Hausdorff topology. And the only thing one has to assume some growth conditions in infinity. So you need that h of x is sort of less than or equal. What the real condition is that it should be bounded, it should be less than parabolas, but we'll assume that it's less than c1 plus x. And the condition is only a one-way condition. This whole thing is very, very not invariant under flipping. It's just an upper bound. There's no lower bound whatsoever. Well, look at the narrow wedge. Okay, so narrow wedges are nice in this business. Okay. Okay, so it's going to be a Markov process on that. And now, what is it? So first of all, if you want to try to guess what it is, well, you might first start, yeah.
A bit naive that the symmetry condition of inverting H seems to knock out that condition.
Yeah, that's a good point, which I won't address. That's right. So you can only invert it if you've got something which once you get it, it's in the class where you're allowed to start again. Yes. Okay. So okay. So what happens? The first thing you could do is just take a KPZ equation because it rescales nicely, right? TASEP, I would not want to try to rescale that thing, but rescaling KPZ under this rescaling is easy, and you just get this. You just get and you should just think, well, they aren't really different. This is basically saying that it's epsilon to 1/2 Ornstein-Uhlenbeck perturbation of this thing. And that epsilon 1/2 is going to 0. And so, well, naively, what's it going to? it's going to that, right? But that's not a very well posed equation. That's the integral of the Burger's equation, and we know Burger's equation is not well posed. Unless you add some conditions like it's going to be a viscosity solution.
So which rescaling are you doing here?
We're doing this.
Standard one?
Always the same rescaling.
I misunderstood.
Yeah.
I thought it was invariant under that.
KPZ is definitely not invariant under that scaling.
Ah.
Yeah.
So what? Explain.
Yeah, so
Oh,
the
I
whole
see.
point is
Right.
that under that scaling, all the normal world which we know of stochastic PDEs is lost, and we've gone to infinity. And now we're in Oz, and we're discovering all these new things. This is, right? There's this new universal process in the limit. That's this H bar, the KPZ fixed point. So the KPZ fixed point is not the KPZ equation. It's the KPZ equation when epsilon goes to 0.
Got it.
Okay?
Couldn't we think of what Martin was saying yesterday, that we look at the parametrized family, and then what you're talking about here is covariance properties of that family of equations, where you take arbitrary coefficients A, B, C, and D in the KPZ equation.
Well, not really, because you don't know what happens as epsilon goes to 0. Yeah.
But just to give a name for this invariance property, that the equation's equivariant, and that's the...
No, I don't know.
Do you lose the constant C epsilon t when you do the rescaling in the KPZ equation, or you add this as a...
Right. So this no. Of course it rescales. So to do this, one has to be very, very careful about what constants one's going to subtract to get the right limit. Yeah. That's very model dependent, and so you have to understand that you say, well, how do you know what's the C epsilon? Well, you're doing it by algebra. You see what's the C epsilon. Okay. In KPZ, you would know what that was too. You just wouldn't know how to do the rescaling. Okay. So, I mean, in TASEP, it's actually very simple. In TASEP, that constant is epsilon to the minus 3/2 over 4. Okay, so, all right. At any rate, the only thing we know about this equation, that's called the Hopf equation, by the way, the integral of the Burger's equation. The only thing you know is what are viscosity solutions. Viscosity solutions are given by some variational formula, the Laxolinic formula. And you can just check Brownian motions aren't invariant. You can just check that it doesn't have any of these distributions. So it's clearly that's not the answer. It's some other magical limit. Okay? So that doesn't help. Okay. So now I'll tell you what it is. Okay. Okay. So the other thing is that unlike other problems in stochastic analysis, it's very odd. It's a Markov process. It's a limit of Markov process, so you expect it to be Markov. It's not true that the limit of Markov process is Markov, but one expects it to be true under physical conditions, and here it is true. One can prove it. It's not easy to prove. So it's a Markov process, and usually we define these things by different equations, basically, right? We've got some equations or some generator or something like that. So this is a very unusual one. There's no equation, and there's no generator. All we have is the transition probabilities. But the transition probabilities are completely explicit. Okay, so let me tell you what they are. Well, okay, let me erase this. Okay, so just like before, all the transition probabilities are going to be given by Fredholm determinants. So F. They're going to be determinants. And basically, the whole thing is just going to be a map, which if you have your initial data, it's going to tell you what's this operator, t x1 through xn. Okay, so it's an operator which depends on t and x1 through xn and your initial data. And once I tell you what's that operator, well, all you have to know is the following. Well, so first of all, I should go back for a second. What's a Fredholm determinant? A Fredholm determinant you should think of as just the operator version of a standard determinant. And well, at least I like to think of determinant as just the product of the eigenvalues. So this thing is just the product of the eigenvalues of this, which is the product of 1 minus the eigenvalues of this. But it's an infinite product, and if you want an infinite product to converge, product of 1 minus lambda I, what do you need? You need the sum of the absolute values of lambda I to converge. So there's a norm on kernels called the trace norm, which is the trace of the positive version of the operator. So you just take the positive version of k star k, take its trace, and that's a norm on operators, which is like L1 of operators. And basically, you can think of that thing as the sum of the absolute values of the eigenvalues. So you need that thing to be finite. So basically, it's a map from the initial data into compact operators finite in this trace norm, which is what we need to describe this thing. Okay. So I'm going to tell you what's k, t, h, x1 through xn. Okay. Remember, it's a n by n matrix valued operator. Okay. Now, the best way to describe it is just kind of strip away the t and then the x's and then the h. And so first I'll describe its dependence on t. Now that's very funny. So d is the derivative operator. Okay? Just the plain old derivative operator. So this is just this operator, the generator of the Airy functions, if you like. And I hope the notation is clear. KT is just the conjugation of that thing by another operator which doesn't depend on t anymore. Okay, so that's how it depends on t. And that's already interesting because that tells you that this system is a completely new thing. It's a completely integrable Markov process. The Markov transition probabilities themselves are a completely integrable system. What's a completely integrable system? It's a system that if you want to know the time evolution, there's a map into some new space in which the time evolution is completely trivialized. That's what a completely integrable system is. And here it is. The map is to this thing, which I haven't told you, but now it's completely trivial, you see? It's a linear flow up there in space of operators. So it's a completely integrable. Okay. So next, I'm going to tell you how it depends on the x's. Okay? So,
All this is for general initial data.
right. All this,
Whenever LAVs turn up,
you'll see it in a second.
yes.
You'll see it all in a second, yes. Okay. Yeah, so H0 here, I guess I'll just say it now. H0 is our initial data. It lives in UC, upper semi-continuous functions. And I'll describe the whole thing. I haven't described it yet. But the map from UC into this is continuous from UC into the trace class. So it's all exactly as it should be. Okay. So now let me tell you what's this guy in here, how it depends on the x's. So remember, it's a matrix. So there's an ijth coordinate. So I'll write the ijth coordinate. So the ijth coordinate of this guy is e to the minus xi d squared. So that's the same old the derivative operator squared. So this is the heat semigroup. K h0 e to the xj d squared. And now somebody should object. Are there any objections?
I'm confused about the time dependence actually. It's a unitary conjugation what you're doing.
Yeah.
Then the eigenvalues are independent of t.
I can't hear you.
The eigenvalues are independent of t, so the Fredholm determinant is independent of t, right?
What is the derivative with respect?
No. Only if r is minus infinity. You see? Yes.
You said there's no generator for this Markov process?
Well, I didn't say there's no generator. I said we don't have one.
Can't you use this formula of conjugation to do some?
Backwards forwards parabolic flow here, is that the problem?
Yeah. Yes. Yeah.
Is it that your generator depends on the initial data? H naught is the initial data?
H naught is the initial data. This isn't a generator. This is very different from a generator. This is a kernel which goes into a Fredholm determinant. It's not the generator of a Markov process. It's something very, very different. So it's sort of like, yes, up in the world of operators, there's this sort of nice generator picture, and then you project down to our normal world with Fredholm determinants to get the transition probabilities. Okay, so as you pointed out, no one ever said that the x's are positive. That's for sure. but this thing has a way of coming to save you whenever you get into trouble. So this operator has a nice kernel. It's just convolution with, okay. So it's a function of u with a bunch of other things that are parameters. Okay, don't look too carefully at this function. But the amazing thing is that it doesn't matter if x is positive or negative. You can solve the heat equation forwards or backwards or whatever you like because of the d cubes. As long as t isn't 0. So as long as t is not equal to 0, it's a group. And there's no problem. So this is perfectly valid because I've always got these guys outside. Okay. Okay, so now, this, even at this level, there's an amazing consequence of all this, which I will write here. So this is something we just discovered. I'm only writing this as theorem because we just discovered it. So this is 19. By the way, all the work I'm describing is with Konstantin Matetsky, Daniel Remenek, and me. And this one is just with Daniel. Okay. So let's take the one-dimensional case. So this is a consequence of where we've got so far. I still have to tell you what's KH, but actually it doesn't matter for this, amazingly. So we just take the one-dimensional guys. And now I take phi is dr squared of log of that. Okay. Now that's the thing. Actually, although Tracy Whittam, did I erase it? I lost the formula for GUE. But anyway, GUE is e to the minus something of q squared. That just says dr squared of log of FGUE is minus q squared, where q satisfies Panlevet 2. So this is the analog. Okay. dt phi plus phi dr phi plus dr cubed phi. That's KdV. Plus dr inverse dx squared phi is equal to 0. It's called Kp. So the one-dimensional marginals of random growth satisfy the Kp equation. Who would have guessed? If you look for the special solutions flat or narrow wedge, they have obvious scaling invariance. So narrow wedge, you look for phi t x r is t to the minus 2/3 c of t to the minus 1/3 r plus x squared over t. Then you'll get an ODE for psi, which I won't write. But it's very, very well known that psi is minus q squared, takes that ODE to Panlevet 2. And if you look at flat, then you look for phi t x r. Well, it turns out you have to divide by 4 because of some funny scalings. T over 4 to the minus 1/3 r. Then you get an ODE again, of course, because you know these things have that scaling invariance. So you get another ODE. And now there's an even more famous transformation. Psi is a half q prime minus q squared. That's called the Mira transform, which turns that equation into Panlevet 2.
What is KH not in this case, in those cases?
Yeah, I'm going to say KH not in a sec. I still have 5 minutes. Okay, yeah. So you see, all this, the way they wrote it, was just a very strange way to write the Mira transform. It's a half q prime because you only integrated once, and then you have a half of q squared. So all the old solution are just special self-similar solution of the Kp equation. Okay. Okay, so now KH, that's the most fun of all. You got 5 minutes. So here's KH. We have our H. Is H naught. And we want to try to probe H. Well, usually in scattering theory, you probe a function by sending in a wave from infinity and asking how the wave's transmitted and reflected, and you use those coefficients and you try to recover your function. But for some reason, this is a sort of mesoscopic problem, so it wants you to scatter with Brownian motions. So I'll start it from U, and I'll go to V. And we send in a Brownian motion, and we ask for it to go, starting at U, to get to V, hitting. That's called hit. Just a second. Oh, sorry. As many times as you want. It just has to hit. Yeah. It just has to hit. Of course, there's some which don't hit at all, but those are the ones which you're excluding. So that probability is called P hit. Okay? And now you think of it as an operator from minus L to L. You could ask the following question. If I know P hit as an operator from minus L to L, can I recover my function H0? It's a good question. It's not obvious. It's true. You can. But this thing's way more greedy. It wants it on the whole line. Now you could just take L to infinity, but now it's clear it wouldn't work. Because if the Brownian motions come in from infinity, they get very blurry in the middle, right? So it tells you to do the following bizarre thing. It tells you to refocus.
Plus sign or both minus?
Minus. Focus at either end into the middle. Okay? Now, yeah, of course you're worried. How can this make sense? But it doesn't matter ever because of these things. Well, even here it doesn't matter even more, and I'll show you. I'll give you an example in a second. 2 examples. You take a limit, and that's KH naught. The limit exists in the sense that this thing is a continuous map from UC into the trace class operators. Okay, let me just show you in 2 seconds that this could possibly make sense. I'll give you 2 examples. Let's do it in our 2 special cases. So, case 1 is a narrow wedge. So in the narrow wedge case, you've been told to go from here to here. In the middle, you're supposed to be below 0. That's the narrow wedge. Right? So P hit, that's easy. You just had to go time L, e to the L d squared. And then you have a projection onto the negative negative line, indicator function minus infinity to 0. So it's that projection operator. And then you have e to the L d squared. That's all it was. So of course I can put e to the minus d squareds on either side. Right? There's no problem. And all you end up with is that the Brownian scattering operator is this guy. And the Brownian scattering operator is that guy. Now you do that junk and you just get the area kernel. It's almost obvious. Let's do another one, and then I'll stop. The other easy one is flat. Flat. So there's 0. And now I want to start at U. And I want to get to V. And I want to hit. No, but we all know what's the probability. Hitting to go from U to V. P hit is just equal to, well, you just use the reflection principle, right? is just e to the 2ld squared u plus v. So now you take the things on the other side and you just get the reflection operator. So the Brownian scattering operator of flat is just the reflection operator, and just give me 1 second. So if I take the reflection operator at time 1, I just get area I get that as my kernel at time 1 after a calculation. And, well, just by black magic, this is equal to 2 minus 2 to the... It's called the scaled area formula. Scaled area formula. So that's why you got that kernel. And that's why the 2 to the 1/3 came in, because it was just hiding that reflection fact. Okay, I'll stop.
We might have time for a couple of questions.
I had a question about your result, this KP equation. So for the pandas A2, normally there's a special boundary condition to select which solution.
That's right.
Is there a way for general initial data to say what that initial
Yeah, because
boundary condition should
so what happens is that this phi has initial data, which tells you to pick out the Hastings-McLeod solution. Actually, if you go back to Hastings-McLeod, that's where they got it from. From exactly that problem. They were trying to solve, so they were looking for the similarity solution of KDV, which is the solution starting with a wedge, which is the boundary condition you get for flat. And if you start with the wedge, you immediately get this Hastings-McLeod solution. So it's just another way to say the same boundary condition. It's sort of simpler in this context.
And you can see for general H0 what that initial...
The initial condition is easy. Yeah.
Time reversibility, does it play any role?
Yeah, that's how we discover the answer. So that's next lecture. Yeah.
All right, if there are no more questions, let's thank our speaker and thank